Hi, in this video we are going to talk about the most important theorem in calculus, and it has a name that makes it seem like the most important theorem in calculus, the Fundamental Theorem of Calculus. Alright, so before we get into that theorem, I just want to make sure that we're clear kind of about what we've talked about so far to do with integrals. So we have really two different kinds of integrals. We have indefinite integrals. And an indefinite integral is the collection of all functions whose derivative is that little f of x. And then we have recently been talking about definite integrals, which look very similar but mean something totally different, right? So the only thing that looks different when you write a definite integral is this a and b, but they mean something completely different. A definite integral is really a sum of all the function output values on the interval a to b. And so in general, that sum represents a number, not a collection of functions like we have for an indefinite integral. Alright, so those two things look very similar but actually mean something different, and why you would do one or the other of those things really are totally different reasons. But the fundamental theorem of calculus is what connects these two things. Okay, so the fundamental theorem of calculus is here in this box. In our textbook, it's stated as part 1 and part 2, and they are on totally different pages and in different boxes. But some textbooks will state them all together. I've got it here just all together, maybe make it a little bit easier to connect those two ideas. Alright, so in any theorem, there is a hypothesis in the theorem. So those are the conditions that must be met in order to use fundamental theorem of calculus. So this applies to continuous functions on an interval a to b. And then the first part here, which is actually called part 2 in our book, some textbooks call this part 1, or the evaluation theorem, the evaluation part of fundamental theorem of calculus. It doesn't really matter which part you call part 1 or part 2. That's not standard. If you look in different textbooks, they'll call different parts part 1 and different parts part 2. Alright, so this tells us basically the connection between a definite and an indefinite integral. It says that if I have, this is a definite integral, so this represents really a sum, that I can find the value of that sum by using an antiderivative. So this is about indefinite integrals, and it says here any antiderivative. So I don't need just one, I could use any. Remember, an indefinite integral gives you all of them, so pick one. And that definite integral from a to b of f of x dx is the antiderivative evaluated at the two endpoints. And we've got some subtraction here, so it's important to note which order those two things are subtracted in. So this upper limit of integration is the number that gets put in first, and the lower limit of integration is the number that gets put in second. Alright, so I'm just going to write a really easy example right here. So if I have the definite integral from 1 to 3 of 2x dx, right? That is actually a definite integral that you don't technically need calculus to evaluate, because this is really just the function y equals 2x, which is a straight line from x equals 1 to 3, and this is a region, the trapezoid. It's made up of a rectangle and a triangle, and it's easy to find this area without needing calculus. But if I use fundamental theorem of calculus to evaluate this, it says I just need to think about any antiderivative of 2x. So that one should be pretty easy to think about. Antiderivatives of 2x are x squared plus c, and I'm going to evaluate that from x equals 1 to x equals 3. So some people use a vertical line here to indicate I'm going to evaluate that antiderivative from x equals 1 to x equals 3. Some people use a vertical line, some people use a bracket. Either is correct. Our textbook likes to use a bracket, and I tend to use a vertical line. Either one is correct. Notice that this theorem says really I can use any antiderivative, so I can really pick any value of c there to use. I could use c equals 0 or c equals 1 or any value of c. And so a lot of times we'll just pick c equals 0. So we'll say I'm going to evaluate the function x squared from x equals 1 to 3. And then I'm going to put the two numbers into the function. So I'm going to put in 3. I'll have 3 squared and then 1 squared, and I'm subtracting them in the right order. So I'm just using the right hand side here. F of b minus f of a, and so I get 9 minus 1, which is 8. And you can verify that that is the correct answer by using some geometry and just thinking about the area of the rectangle. This is from 1 to 3, and you can figure out these points here. You can find the area of that rectangle and area of that triangle and verify that you do get 8. So what I just did there is not a proof of this theorem, it's an example of using that theorem. Notice the function that I chose here is a nice function, continuous everywhere, specifically continuous on the interval 1 to 3, and it's very easy to write down an antiderivative. We will certainly look at functions where the function maybe isn't continuous, and then what do? Or maybe it's really difficult to write down an antiderivative, but those were the two key things I needed to be able to do here: continuous function on that interval, and I need to be able to find that antiderivative, and then I just use that theorem to get the value for that definite integral. This part of Fundamental Theorem of Calculus, our book calls part 2, and again, that doesn't really matter. I put it first here though because this is the version that you are going to use over and over and over again, particularly if you continue in calculus. So this is one of those big deal theorems that you will use a lot. The second part here, the second bullet point, generally if I ask students that are in Calculus 2 or 3 to tell me what Fundamental Theorem of Calculus says, they will state the first part here, what I have in the first bullet point and what I've highlighted. They often forget about this other part. So there is another part here. Our book calls this part 1. But it is something that you probably won't use as much, and so students tend to forget that. So we'll talk about some of this and look at some examples in some later videos, but I want to just emphasize here that this is a function, little f of t, and I am integrating that from a, where a is the endpoint of our interval, but x really is a variable here. And so I'm being asked to integrate that function and then differentiate that function. And basically what this theorem says is that the differentiation undoes the integration. And so this is used a lot in proofs of other things. And the key idea here is that the differentiation undoes the integration. And we will look at some examples of that kind of basic version and then slightly more complicated version of using that theorem in some later videos. But again, the part that I highlighted is the part that you're going to use over and over and over again. So that is the part I want to focus on for right now. And I want to talk a little bit about the proof of what our book calls part 2, but is the part I've highlighted up here. And I don't expect a student in Calculus 1 to necessarily be able to do this whole proof, but I do expect you to understand that it is something that can be proven and the idea of what's happening in this proof. Okay, so anytime you're going to prove some sort of theorem, you want to be sure that you clearly state at the outset what are the givens, or what is the information that you are starting with. So that is the if part of the theorem. So I'm going to start with some function, and that function needs to be continuous on an interval. All right, the other thing that I need at the beginning here, if I'm going to prove part 1, is I need to be able to find an antiderivative. So I'm going to use the notation that's here in the theorem, and I'm going to use capital F of x, and I'm going to say that that's any function whose derivative is little f of x on that same interval. That's what it means to be an antiderivative. It's a function whose derivative is the original function. All right, so a couple of key things that we want to make sure that we understand that that tells us. If capital F of x is a function that has a derivative, little f of x, then that means that capital F of x is continuous on that interval. And part of the reason I stated that is because we are going to eventually use mean value theorem, and these are the two conditions that are necessary in order to be able to use mean value theorem. All right, but we're going to think about really two different things here. One is the definition of the definite integral, and so I'm going to start by making a partition. And when we talked about definition of a partition, remember that we start by letting our x naught be the first endpoint, the leftmost endpoint. And then I choose x1, x2, and so on up to xn, that is the right endpoint of our interval. And then I'm going to look at each subinterval. And in each of those subintervals, because the original function is continuous on the whole interval a to b and differentiable on the interval a to b, the interior, then it's also continuous and differentiable on these intervals. So we can apply mean value theorem to say that the capital F of x then, that is continuous and differentiable, would have a value of c that satisfies the mean value theorem. All right, since I know that capital F of x is a function whose derivative is little f of x, I can rewrite the left side there as little f of c sub k is the right-hand side. All right, and then a couple more steps here, and we are ready to actually complete the proof. So this denominator here, notice that that is a delta x sub k. So I can multiply through to rewrite that as f of c sub k times delta x sub k is equal to f of xk minus f of xk minus 1. Okay, so I basically have created a partition and I have chosen a point in each subinterval. So I can write down my Riemann sum. And because I have this previous line here, the f of c sub k times delta x sub k is going to be equal to the capital F at x sub k minus the capital F at x sub k minus 1. I can just replace that in my Riemann sum. And now I'm just going to write out what this sum is. So I'm going to start with k equals 1. So I'll have f of x1 minus f of x sub 0. I'm plugging in k equals 1. And then I'll have plus, then I'll plug in k equals 2. F of x2 minus f of x2 minus 1 is 1. And I'm going to keep doing this until I get to the end. All right, and then look at what happens here. I've got a bunch of stuff added up, but notice that I've got some terms that are going to cancel. And I've written a ... in the middle, but you should understand that in that ... are a bunch more terms that also will cancel. And so in each of these little groupings of f of xk minus f of xk minus 1, I'm going to have some cancellation with an adjacent grouping until I get to the end, and then the only one that won't have a cancellation are going to be the f of x naught and the f of xn. So at the end, everything collapses, and I'll end up with, I'm going to rewrite the terms in a different order here because of the subtraction, f of xn minus f of x naught. All right, and then going back up here to our partition, notice that x naught is a, the left endpoint, and xn is b, the right endpoint. So I end up with here f of b minus f of a. All right, I'm not quite done with the proof here because I need to take the limit as the norm of the partition approaches 0 of my Riemann sum. All right, so in my previous work here, I have showed that this Riemann sum is equal to f of b minus f of a. So if I take the limit as the norm of the partition approaches 0 of one of those things, that should be equal to the limit as the norm of the partition approaches 0 of the other thing. And if I just think about what these two things are, on the left here, that's the definition of the definite integral from a to b of little f of x dx. And on the right here, when I take the limit as the norm of the partition approaches 0, there is no x in here and there is no partition here. The norm of the partition is not here. So when you take the limit as something approaches 0 of something that does not involve that thing that's approaching 0, you just get the thing that you have on the right hand side here. Alright, so that completes the proof. So I've proved part 1 of the Fundamental Theorem of Calculus, or what our book actually calls part 2. Alright, so I don't expect you to be able to recreate this proof. If you go on and take math and become a math major, maybe you will need to be able to do that. But for right now, what I expect you to do is understand that it is something that can be proven, and maybe understand that mean value theorem is kind of the glue that holds those two parts together. But most of the problems in your homework are going to be like the example that I did here in the middle of the box, where you're taking a function and you're actually using Fundamental Theorem of Calculus to calculate the value of that definite integral. Alright, so watch some more videos for some more examples of those.